Hello everyone, today I'm going to introduce Homework 2 Part 2, which is about conditional lantern diffusion model. In this homework, the main goal is to understand how lantern diffusion models generate images more efficiently and how conditions can be used to control the generation results. We will first review the limitation of DDPN, then introduce lantern space, LDM, conditional LDM, and finally explain what you need to do in this assignment. First, let us briefly review DDPN. DDPN is powerful, but it has two main problems. The first problem is that it is expensive when we apply it to high-resolution images. This is because the diffusion model works directly in image space, so the model has to process many pixels. The second problem is that DDPN is slow during inference. It usually needs many denoising iterations to generate one image. So even though DDPN can generate high-quality images, the cost becomes large when the image resolution increases. This motivates the ideas of lantern diffusion model. So instead of adding noise directly to the original image, we can add noise to a lantern representation. The key idea is that lantern space keeps the important semantic information while discarding redundant pixel level details. For example, for cat image, the lantern representation does not need to store every exact pixel. You only need to preserve the meaningful information such as object structure, color distribution, and general appearance. So compared with image space, lantern space is smaller and more compact. This made the diffusion process more efficient because the model denoises a complex representation instead of the full image. Now let's introduce lantern diffusion model. LDM is a diffusion model that operates in lantern space of a pre-trained autoencoder, usually VAE. During training, the input image is first passed into the VAE encoder. The encoder compresses the image into a lantern representation. Then we add noise to this lantern representation at a random time step. The diffusion model is trained to predict the noise added to the lantern feature. So the training target is still noise prediction, similar to DDPN. The difference is that the input is no longer a noisy image, but a noisy lantern feature. This is why LDM can be more efficient than DDPN. During inference, LDM starts from random noise in lantern space. The diffusion model gradually denoises this lantern noise step by step, just as DDPN. After the denoising process is finished, we get a clean lantern representation. Then the VAE decoder converts this lantern representation back into image space. So the full inference process starts from random lantern noise, denoise it using diffusion model, recover the clean lantern feature, and finally decode it into an image. It is the basic highlight behind lantern diffusion. Next, we move from LDM to cLDM. The C stands for conditional. A conditional LDM incorporates external conditions to guide the generation process. For example, in mixed, the condition can be a digit label such as 0, 1, 2, and so on. In a dataset contains celebrities called celeb8, the condition can be facial attributes such as smiling, male, blonde hair, eyes glasses, or young. The condition is usually embedded into a feature vector and then inject into a unit or diffusion model. So the model does not only ask, how do I denoise this lantern? It also asks, how do I denoise this lantern so that the final image matches the given condition? And the training of cLDM is the same as the LDM. It is similar to LDM, but we add one more input, the condition. First, we take the image and pass it through the VAE encoder to get the lantern limitation. Then we add noise to the lantern limitation at random time step. At the same time, we provide a condition to the diffusion model. The diffusion model receives 3 pieces of information: the noisy lantern, the time step, and the condition. Its job is to predict the noise that was added. So the condition helps the model learn the relationship between the label or attribute and the generated image. And before training the diffusion model, we need to train the VAE. In the VAE training, the image goes into the VAE encoder and becomes a lantern feature. Then the VAE decoder reconstructs the image from the lantern feature. The goal is to make the reconstructed image close to the original. At this step, the VAE learns a useful compressed representation of the image datasets. This pre-trained VAE is important because the diffusion model will later operate in this lantern space. If the VAE reconstruction quality is poor, the final generated image will also be limited. After training the VAE, we train a noise predictor. In this stage, the VAE encoder is usually frozen. We use it to convert image into lantern representations. Then we add random Gaussian noise to the lantern feature at a random time step. The diffusion model takes the noisy lantern, the time step, the condition as inputs, and predicts the noise. The loss is usually mean square error between real noise and the predicted noise. So the model gradually learns how to remove noise from lantern representations under different conditions. And during inference in cLDM, we do not need the original image anymore. We start from random noise in lantern space and provide a condition. For example, if the condition is a cat, then the model should generate an image that looks like a cat. If condition is a smiling, the model should generate a face with smiling attributes. The diffusion model repeatedly denotes the lantern variable while being guided by the condition. Finally, the VAE decoder converts the final lantern representation into an image. So compared with normal LDM, cLDM gives us more control over generated results. So now let us move from theory to actual homework. In this assignment, we are going to use conditional lantern diffusion model to generate images. There are 2 data sets used in this homework. The first one is mixed, and the second one is cerebral face attributes dataset, which contain lots of face image. Cerebral A is also difficult because it uses RGB face image and contains more feature violation. And here are the main tasks in this homework. First, low mix dataset. Train the VAE, plot the loss, and train the cLDM. Then generate image in 5x5 grid. Then plot the loss of the cLDM. Then we do this whole procedure in the Cerebral A dataset. As for basic requirements, the total score is 70%. For mix, you need to plot a loss curve and the 5x5 samples. And for Cerebral A, you need to train in RGB image and explain your implementation and provide loss curve 5x5 image sample. For the advanced part, it is worth 30%. You need to compare the difference between DDPN and DDIN. and implement DDIM. Next, you need to train 5 conditions on syllable A, discuss the weakness and improvement. And in the basic session, you only need to train 2 conditions, which is or 1 condition, which is smiling and non-smiling. And so, if for the advanced parts, you need to train the 5 conditions, and the condition you can choose any condition you think it is feasible. And the last one is benchmark on syllable 8, and we use one metric to evaluate your model performance, which is FID, just as like DDPM. And this metric is the lower the better. And score will be judged based on how much you outperform your classmate, which is determined by ranking. So, for example, FID will rank based on your FID score, and do the scoring based on the ranking. And just like in the part 1, we provide a template code that on the Google Colab, and also provide a FID calculating function that help you to do the work. And since in the advanced part layer, you may be doing 5 condition cLDM. So it's no worry that because we only test the smiling part. We only test smiling and non-smiling, and calculate and wait them to calculate your FID score. And for the submission, the deadline is on May 21st, 11:59 p.m. and there will be 10% deduction every week of late submission. And you need to submit your code in Jupyter Notebook formats and give me a Colab link that fork from the template. And also, you need to submit reports and the model file, so that we can rerun your code. And then your lib file into this format: student ID, your name, homework 2-2, and submit to E3. And last, please do not submit code copied from the internet. If you refer to code from GitHub or other open source project, you need to cite the result properly and comment on that code. Otherwise, there may be a penalty of 20% or more. And I will recommend you to use your GPU conservatively because of the huge size of the syllable A datasets. Maybe you can use CPU mode when you are in the coding and verifying, and if you want to training, you then switch to the GPU mode. And since there's maybe around 4 to 5 hours GPU usage time limit. Once you reach that limit, you have to wait 1 or 2 days to resume your work. And so maybe that policy will delay your homework process, and then the deadline, and then it says the deadline of this homework. So I also recommend you to start earlier, just in case that the GPU you run out of the GPU and have to wait. So yeah, so that's it. Thank you for your listening.